Hi, my name is Kurt Yonke. I'm from ME65. My faculty advisor is Dr. Chai-Jun Sung, and my project is the soot measurement of RD587 and its surrogates under engine-relevant conditions. The overall goal of this experiment is to create a setup that can be reused for multiple fuels to determine the soot volume fraction under viable conditions. The deliverables for this project are to research a setup, design the setup, and then for RD587 and its surrogates, determine the sooting propensities or the sooting tendencies of the fuel under different conditions. This will produce a set of experimental results that can aid in the development of chemical kinetic studies. The figure above depicts a rapid compression machine. The right side of the machine is the pneumatic section, the middle is the hydraulic section, and the left is the reaction chamber section. A typical experimental run begins by retracting the piston using pneumatic force in the pneumatic section. The piston is then locked into place using the hydraulic section using hydraulic pressure. When the hydraulic pressure is released by a solenoid, the piston flies forward at the driving pressure and compresses the mixture in the reaction chamber section. This is able to achieve low to intermediate compressed temperatures and compressed pressures up to 80 bar. The data obtained from the reaction chamber is a function of the temperature of the compression, the pressure of the compression, and the equivalence ratio of the chosen fuel and oxygen diluent. This serves as a way to validate chemical kinetic models. The time between the end of compression and combustion is the ignition delay time, which is the primary form of data achieved using a rapid compression machine. This effectively models a single stroke of an internal combustion engine. As discussed on the previous slide, this is a typical pressure trace, or the graph used to obtain the ignition delay time. It can be seen the end of compression and then the pressure rise due to ignition. The difference between the two is the ignition delay time. This is the compression that occurs is relatively close to adiabatic compression. In general, these are the different relations between the different variables that can be changed and their effect on ignition delay time. The compression of the air-fuel charge in the reaction chamber can create soot. However, the temperature must be high enough to initiate soot formation. Other variables can be changed in the reaction chamber to vary the amount of soot production. In general, pressure rises, soot production will rise. Fuel-air equivalence ratio, once increased, will increase soot production. However, rising temperatures increase all reaction rates. The determination of how the soot production is affected will be varied by if the oxidation rate outpaces the soot formation rate, or vice versa. This figure depicts the prototype light extinction setup that was generated. The series of lenses, filters, and mirrors are chosen to combat mechanical vibrations, beam steering, and light generated during combustion. It begins by the laser light leaving the laser, going through a neutral density filter, a lens, bouncing off a mirror, passing through the combustion chamber, back onto another mirror, through another lens, through the interference filter, and then into the photodiode. This picture depicts the constructed prototype from the previous slide. The laser can be seen on the far table, and the different components can be seen surrounding the reaction chamber. The figures on this slide depict the data that is typically produced using the experimental setup. The blue line is the pressure trace using the pressure transducer. The orange line is the light intensity from the photodiode. It can be seen on the first plot, the soot light attenuation as the pressure rises in the reaction chamber. The beam occasionally moved off the detector during compression, and that can be seen as beam wander noise. Otherwise, the prototype setup performed as expected. The data is gathered in a LabVIEW VI and then post-processed in a custom Python script. To process the light extinction signal, the following formula is used. It is used to calculate the soot volume fraction from the laser light intensity signal. The following are the variables that are in the formula. The I/O is tuned with the neutral density filter, acting essentially as sunglasses for the laser so attenuation is acceptable. If the laser is too powerful, the photodiode cannot sense attenuation by soot. Using the equation on the previous slide and the graphs above, the soot volume fraction was calculated. It can be seen that for 95-degree preheat of the system, there was a significantly lower soot volume fraction in terms of parts per billion. The figure above depicts the final design used to produce data. It added an integrating sphere instead of a plain photodiode. This was added to overcome beam steering and vibration from the machine, seen on the previous slide in the plots.